Okay, well, it's a great pleasure to have Zoltan Fodor, who is now, I guess, spending part of his time at Penn State, to tell us about the magnetic moment of the muon status report.
Thank you very much. First of all, thank you very much for the invitation. It's a great pleasure to be here and to report on the magnetic moment of the muon. The story is actually old in some sense and extremely exciting. So let me start with a little bit of a history. So this is a plot, let's say, from 2006. Brookhaven measured the anomalous magnetic moment of the muon. So this is the 8th, 9th, and 10th digit of the magnetic moment, actually the half of it. And the green band shows us the experimental result. And already at those years, there was a 2.2 sigma discrepancy between the standard model and the experimental finding. And that gave hope to people that we will see in some new physics here very soon. And indeed, a few years later, actually 15 years later, Fermilab measured the magnetic moment of the muon, and the error became smaller. And on the very same day, when this result was presented, Nature published our paper, the lattice calculation of the magnetic moment of the muon. And as you see, it was in a fairly good agreement, 1.5 sigma. And that somehow spoiled the game because there was a white paper written by 134 physicists. Actually, they wanted to have 137, but couldn't manage that. Based on E plus E minus hadronic cross-section. I will say a few words on that later on. This method is called the R-ratio method, or the dispersion relation method, or the theory initiative result, or even the theory consensus value. I don't like that name because I certainly didn't agree with that. And luckily enough, yeah, perhaps, or I didn't belong to the 134. Yeah, and I mean, science is not a democratic institution. But, a consensus is not necessarily something that brings us further on. And what you see at those days, it was a 4.2 sigma discrepancy. So that's why there was a huge excitement about that. Even in newspapers, it was believed, you need 5 sigma to get that, to have a discovery, a new force, a new physics, and 4.2 is almost 5. So let's celebrate. And I remember there was this press conference during COVID with 5,000 Zoom participants, 5,000 because that was the maximum number. And even the New York Times held a story on the opening web page for 2 weeks, which is very rare in particle physics. And these experimental result and the BMW result, which is this Budapest Marseille Wuppertal result, was selected to be one of the breakthroughs of the year in 2021. The white paper was based on, as I said, E plus E minus collisions. Here I show you 2 of them, the Babar and Chloe. These were the most dominant results which went into that white paper. And if we go a little bit even further, in 2023, Fermilab improved the statistics, the error became even smaller, and now the tangent was 5.2 sigma, so beyond the discovery level. But nobody was speaking about discovery anymore. And that was because lattice spoiled the game somehow, And there was a experiment CMD3 from Novosibirsk, and they found that actually even the E plus E minus can be consistent with the experimental finding of the direct measurement of the magnetic moment.
So what's going on here? Are these other experiments filling in data for the dispersion relation?
Yes, so these experiments are going into the dispersion relation, but CMD3 is later, so it didn't go into the white paper 20. And the tau was not taken very seriously for a long time. And here I just want to show you that these two dominated the white paper. But actually, even those days, there were some signs that there are some problems with that, because in some energy regions, the Babar and the Chloe results were in contradiction with each other.
But why paper didn't do CMD3?
No, they didn't. CMD3 came later. That's why it was so bad. Yeah. And that brings me to May 2025. The white paper, the people increased their number from 134 to 220, if I counted correctly. And they omitted the dispersion relation altogether. So you see that the white paper 20, which was here, is now here. Right? And that's our result. You don't see it because it says unpublished. Some of the results are unpublished. The white paper came out yesterday on the archive. And this is our result, the gray band or the pink band thing, and agrees completely with the experimental result on the 0.2 sigma level. So we had difficulties to put here the error.
But they're going to just announce next stage of experiment.
Yes, next Tuesday, Fermilab is announcing the new result, and that will make this green error probably even smaller. Yeah. But I don't know how much. So, but I will be there. I will watch that next Tuesday. And after my talk, I can tell stories about that meeting on Tuesday. So this is the latest results of the BMW collaboration. This is the white paper. And now there are, let's say, two other latest results from the RBC, UKQCD, and the MINDS collaboration. And they all agree with each other and very far away from the original white paper result. So this is the take-home message, and let me go into a little bit more detail. So here is my outline, and when I'm discussing these things, I'm going to tell you the inputs into these things. So the experiment, it's an input from Brookhaven and Fermilab. They are in complete agreement. Luckily enough, it is statistics dominated. That means there is nothing you don't know and might make a big difference. And as you said, you pointed out, the final error of Fermilab will be further reduced, data on tape, and on Tuesday it will be announced. Then we have seen the data-driven method, or the dispersion relation, or R ratio method, or theory consensus method. They have hadronic E plus E minus, thousands of data points. I made these analyses too, and I used 4,549 cross-section values. Unfortunately, it is systematic dominated. The systematics are 4 times larger than the statistical, which perhaps explains a little bit that it is possible that the systematics are underestimated, and that's why you have these 5.2 sigma effect.
But just the observations that CMD2 and CMD3 so different, it's you also got both systematic.
Yes, absolutely, absolutely. So it's a very good point that CMD2 and CMD3, which I haven't shown you here, but I have some slides on that too. They were very, very different. It's a hard question to believe the method at all. It's systematic. But there is a lattice, and we have only 4 quark masses, and that's all what we put in, and the fine structure constant. You don't need anything else. You don't need the 4,549 data points. And as I will show you, the systematic uncertainties are about the same as the statistical ones. So far, so good. So the experimental result of the Fermilab is here. What we should remember is this number 2.4 in the last digit. So this is 10 to the minus 10 times 2.4. So I will list all the results in units of 10 to the minus 10. So here, the important message is 2.4, and this is equivalent to a bathroom that is sensitive to the weight of a single eyelash. And that agrees fully with the Brookhaven experiment. And if you combine them, then you will have a 2.2 element. So remember this number 2.2. The target uncertainty is 1.6. We will see on Tuesday whether they reached it. Probably it will be even better. And there is a J-Park experiment which is in construction. I have seen that. So they originally wanted to start in 2024. Perhaps they will start in 2026. We will see. So here is the experimental setup. So pions are produced at fixed target. PP is going to P plus N plus pion plus. And pion decay through weak interaction, and they are producing highly polarized muons. These muons are then sent into this storage ring, and they are going all around. They are precessing. The precession is shown by the green arrow, and the velocity is shown by the blue arrow. And since the precession is a little bit faster, so you see that they are going around with a given frequency. And when they decay, the calorimeter can detect the produced positons. And sometimes they are pointing to this direction, sometimes they are pointing to the opposite direction. So you will see an oscillating pattern, and based on the oscillation frequency, you can determine the difference between the precession and the circulation frequency, and that gives you the magnetic moment of the muon. In the theory, we have 3 interactions: QED, the weak interaction, and the strong interaction. And as I mentioned, these 134 physicists, which the number increased to 220, wrote this paper, white paper 2020 theory initiative. And here are the individual contributions. As you expect, QED is far the largest, because the particles involved are far the lightest. The electroweak is the smallest contribution, again, because the particles W or P are heavy. And QCD, the hadronic scale is somewhere between. And that's the total with an error of 4.3. That was in the white paper. And as you see, QED gives you 0 error, the electroweak gives you essentially 0 error, and all the error is coming from this. And since this dominant error 4.3 is coming dominantly from the vacuum polarization. So in the white paper, 4.0 is coming from the vacuum polarization. In the back 2020 white paper, and as you will see in the BMW result, in the lattice result, that is 3.3. So how does it go? We have these E plus E minus in activation, photon, and it goes to hadrons, and then you normalize these hadronic cross sections by the mu plus mu minus cross section. You use the optical theorem, which connects these vacuum polarization with the hadronic total cross section. And we have 60 years of experiments, CMB 2 or 3, SNDB as Chloe Babar, here is the R ratio. And you use some kernel function, you use some analytically known kernel function, multiply it by this R ratio, integrate it, that gives you the vacuum polarization contribution from the hadronic sector to the magnetic moment of the muon. Again, the white paper had 4.0 on this, using this technique, which was 0.58% error. And today, or yesterday actually, the 2025 white paper result is 713. So the jump of 20 units, several sigmas. What you also rarely see that the error increased by more than 50%. And the technique they used is not at all anymore this R ratio method, nothing of that, but somehow lattice averages in various segments of the lattice approach. So let me move to the lattice, yeah? So we are calculating a current correlation, the electromagnetic current, and then we multiply it with another kernel function, which is known again, and that's what you have. So this is the integral, what you have to integrate. And once you integrated that, then you have the contribution to the magnetic moment of the muon. Here I show you with red points the 2017 results of the BMW collaboration, and blue points the 2020. And as you see, the errors are much smaller as time goes on. I mentioned that the white paper is using several lattice groups in different windows. It means that you can cut these correlator from 0 to 0.5, from 0.5 to 1 Fermi, from 1 Fermi to 2.5 Fermi, or whatever. Various lattice groups have results in these segments, and then they average them segment by segment or window by window. That's how they got these 6.1 as an error. So that brings me to the BMW set. That's our lattice collaboration. We had 7 lattice spacings from 0.13 Fermi to 0.048 Fermi. That's the newest one. That's the new thing compared to our 2020 result. The box size was usually 6 Fermi, but we also have 11 Fermi to study finite volume corrections. And here are the quark masses. So this is the light quark mass, or a proxy for the light quark mass. This is a proxy for the strange quark mass, normalized by the physical light and physical strange quark masses. So the physical point is 1, 1, yeah? And we are bracketing them with various lattice spacings. So there is no physical mass extrapolation or chiral extrapolation, which is the old-fashioned word for that, but we are really working with the physical processes. And here are the so-called beta values, which define the lattice spacings. Here are the lattice spacings, and here are the lattice sizes with the number of configurations. The largest lattice size here is 128 times 192 on not anisotropic lattices. Let me mention that the CPU demands scales as e to the minus 8. So if you want to have a twice as fine lattice, then the numerical costs are 2, 4, 8, 16, 32, 64, 256. So you have to be very careful. Because no granting agents to do a grand Fourier project, which takes 256 years. And this is the final result for 2020. Here you have various graphs, one and a half dozen of graphs. So everybody can prove or disapprove them if the errors are correct, and 6 of them out of the 1.5 dozen, 6 of them should be out of the 1 sigma range. And that time we got an error of 5.5. So remember these 2.2, that was 5.5, and the value was 707.5. This was the statistical error, and this was the systematic. And as you see, the systematic error was still twice as large as the statistical one. So there was a need to improve the systematics. And that's the picture when we unblinded our results from 2000 to 2024. Everything was done in a blinded way, so we didn't know what the result will be. We had a meeting, Zoom, various places on Earth, from Australia to the US, and unblinded the result. So you know what blinding and unblinding is. It's also used in medical research. We are using double blinding. You know what double blinding is? Anybody? No?
Both times.
Both times, yeah. So the classical meaning is that neither the doctor nor the patient knows whether he's going to get a real medicine or not, but a friend of mine who's a cardiologist said the double-blind technique in medicine is when a gynecologist and a surgeon are analyzing an electrocardiogram. That's not the point. Anyhow, that was also somehow double-blinded because it was 2 steps. So if somebody knows some factors, but didn't know the function which these factors were plugged in, and somebody else knew the function, then it was an unblinded. And that's the result what we had. So these are the contributions which we improved. The others had so small errors that there was no need to improve them. These had the largest errors, and then we improved them. And the result was, that's what you find on the archive, 714 with an error of 3.3. In the meantime, one of our referees suggested that we should use another case setting. We used another case setting, and it slightly moved away by, I think, 0.3 sigma. So it's irrelevant. How these improvements were carried out, I show you instead of showing all the lattice details. This is perhaps more instructive. So in 2017, we had the blue columns for the error, and the statistical, finite size, continuum limit extrapolation, physical point, and isospin breaking. And as you see, the blue, that was 2017, has the largest error in the finite size case. So that's why we finished a dedicated large volume simulation. So instead of having 6 Fermi box, we increased it to 11 Fermi. And in 2024, we separated the so-called tail contribution. If there will be any question, I will be happy to answer that. And if you look at the 2020 results, the green ones, then the finite size was already smaller. The largest was the continuum limit extrapolation. And you can get closer to the continuum limit only if you get closer to the continuum limit by an even smaller lattice spacing. So that's why we put a 0.48 Fermi lattice spacing into our samples. And if you look at, again, you remember that there was a drop in the statistical signal in our calculation because we used an O2O propagator. And in 2024, we even separated the tail, and a little bit we worked on the scale for physical point and the dedicated isospin, but they were already tiny. So this brings me to my final slide, which you have seen already. So this is the white paper of 2020. This is the white paper of 2025, actually yesterday. And there are two other lattice results. Which are not BMW. This is the BMW 20. This is the BMW 2024. As you see, the errors here are considerably larger. What you see here is the error of the direct measurement of the magnetic moment is pretty small, and it will get even smaller. And the old technique used the white paper was 5.2 sigma away from the experimental value of the direct measurement of the magnetic moment. So the dream that we see here, a new interactions and new physics is probably gone. But nevertheless, we have an agreement between an experimental measurement, which is the magnetic moment, and quantum field theory, now on the 11-digit level. So we had QED here with a large contribution in many loops and diagrams in the standard renormalization procedure. And if you did anything wrong there, or if the QED was wrong, then you would see it immediately. Even the same for the weak theory, though it is a very different theory with its spontaneous symmetrical thing. And that is QCD had a very different formulation of the quantum field theory, and we had a non-perturbative renormalization there. And if you add up everything, then we have a 0.3 sigma agreement. Of course, that BMW result is just one result. Other groups should conform or refute, and it is done by other groups now. And I'm pretty sure that in the coming years, the errors will be better and better. And they will be corrected further on. So that's my last picture or last slide, and I thank you for your attention.
Thanks a lot, and congratulations on this amazing agreement.
Well, we would have been happier if we found a new physics.
But just looking at the trend over the past 5 years, it's sort of drifting.
Yeah, absolutely.
So and the new latest results are even.
From the other groups.
Yeah, from.
Yeah, but they agree with 1 sigma level with us, so I'm.
But just extrapolating the time dependence. It seems like it would still drift.
You mean that there is a hope here, yeah.
I mean, just go to 210 maybe.
Yeah,
I don't know.
yeah. I mean,
What do we know?
I mean, it is not like an extrapolation in time. I think it's the extrapolation in time has to include the errors. And this is far the smallest errors.
I guess the lesson is that our estimates are very treacherous. Carnegie?
I wonder, in terms of comparison with other like the group, that what is your advantage? Because it's clear that you made kind of very important prediction early on, like I don't know, is it technological or because you certainly will very much depend on us.
Yeah, I mean, when we publish these results, sorry, these are some data slides. So when we published this result, nobody believed us, and we were mocked. And
I believe you.
did you really? And you didn't believe the white paper, the 134 pages.
Right.
Yeah. Okay. Good. Okay. Thank you. I didn't know that. I didn't know that, but thank you very much. So let's say many people didn't. So those people who were working in these white paper for the dispersion relation, they, of course, they didn't believe us because they thought that they have the 5 sigma. They will have new interaction.
No, but it's a different, it's not about comparison different lattices, right? Because they use a different, approach, right? I mean, P plus and minus was the place. Right? And you do a deep prediction, if you like, for a plus and minus annihilation, I would say, not just for magnetic moment, because we essentially predict in the section for plus and minus for proton, and it's independent compressed.
Yes, yes. But what was the advantage? As I shown you, if you make an error of the lattice space by a factor of 2 to the large, big error, yeah, then you are making a project which is 256 times more expensive, and nobody can do that. So it's careful planning, what can be done within a few years, with what precision, and what ingredient here or there should be improved or done. That's what I try to show you with these improvement blocks of the errors. And I don't know what our advantage was, but
Were you ahead in coding or GPU coding?
oh, absolutely,
Yeah,
absolutely. So these are not just GPU codes. They were produced on Blue Jeans and on machine. So not just GPU, really machine. So they tried, that's also one advantage. They try to get every block floating point operation of your computer. That's another advantage. But many small things. So,
it'd be nice to be able to declare victory and point at something that was wrong with the past. I could just let us far enough for the predictions to be able to see to do the forensics and see what went wrong and then we just about this approach.
I mean, I was very skeptical of P plus C minus. I made on myself. I got exactly the same result for these people got 4 digits and the error 3 digits. Everything was the same. But along the fact that there is a discrepancy between Babar and Chloe between 600 and 900, if I remember correctly, MEV, which was 3 sigma, yeah, and then saying, okay, then there is an error inflation technique which we are using, then we inflate with the error, and then we got something which was here as not good for me. I mean, it was certainly some wishful thinking here, that we have to have the 5 sigma and the Amilab must find the root of correction. But these are more sociological considerations then.
Okay, well, maybe we can continue the discussion over coffee. So let's thank Zoltan again.